Hello everyone, hi students. I hope you are all doing good and life has been great. So now we will be discussing a topic on physics that's a key important concept when it comes to your competitive exams or your board exams, and understanding of this concept can fetch you a lot of marks. And not just speaking of marks, it's a good concept and it's actually fun to learn. So basically, it's a recap of already what we did in class. So if people who have done my class, they will feel a little more comfortable watching these videos. But anyway, if you are thorough with the concept after watching the videos, you can be sure of it that you will be thorough of it. Okay. So today we will be discussing about the concept of light. Okay.
Hello students, today we will be learning about a concept of light. So what is light basically? When you are in your lower standards, then light is treated as ray till your class 10s are concerned. So we will learn about ray optics and that's the scope of our syllabus. But is light really a ray? When you go towards higher classes, you will learn that light is also a wave. Now what is a wave? All of you have visited a pool at some point of your life, right? When you throw a stone on the pool, it creates ripples in water, and this ripples travels, right? The ripples tends to grow bigger and bigger by traveling, right? So this is basically what a wave is. So light is also a wave. Furthermore, they tell you that light is also a beam of photons. Now, how is it possible to be all the three things at the same time? Turns out that light is all the three things, and depending on the context which you are in, it behaves that way. So for experiments such as reflection and refraction, today you will learn about refraction. So for these experiments on ray optics, the assumption that light is a ray holds true. For wave optics, this assumption of ray does not hold true, and you cannot prove those experiments using the ray concept of light. For those experiments, you need to treat light as a wave. And also, light is a beam of photons. So you have all seen X-rays, right? X-rays, if you are interested, you can Google out that X-rays actually work similar to a concept called photoelectric effect, and they treat light as a beam of photons, right? They treat light as a beam of photons. Okay. So to understand this by an analogy, suppose you have your real name, you have your roll number, and you have a nickname. So you will respond to all these three uh, contexts depending on who calls you, right? So if your friends call you, you will respond by your name. If your family members call you, you will respond to your nickname. And if your teacher takes your attendance, you will respond to your roll number. Similarly, depending on the experiments we are doing, we treat light as a ray, as a wave, and as a beam of photons. But light is light. Okay. If this concept is clear, let's dive right into the next concept. Okay. So in physics, generally, we we take a small assumption, and based on that, we build a map of things. We actually observe a lot of things based on this observation, this assumption, and that's how we learn different things. But what people generally tend to do in lower level physics in your classes, that they learn different various concepts, and they try to remember all these concepts without building a connection between them. So generally, they forget these concepts after a certain point of time. So what I will do is, I will make you guys build a small assumption, and on this assumption we will build a map of physics. Okay. Now let's try and build a map of light. Okay. So firstly, our assumption is, and I will write this in bold, that light is always in a rush, right? It is always in a rush. It's in a hurry, and it travels through the quickest path. Okay. Now this quickest path is not generally always the shortest path. It need not to be the shortest path. Now why? So if you have two places in your city and you need to go from this place to this place, suppose this road is very crowded and has a lot of traffic. You will not prefer the road, although it's the shortest road, right? You will prefer a quicker road, right? With less traffic. it might be that this road is greater in distance, but if you travel through this road, you will reach quicker from this point A to point B. Okay, so light is similar. It tends to travel in the quickest possible path. Now, this assumption actually has a name, right? This is actually called Fermat's principle of least time, right? And this is the only thing you need to know in order to do any experiments or to understand any concepts of ray optics. This is the only thing that is needed, nothing else. Okay, so if you know that light is in a rush and it travels in the quickest path, you know everything about ray optics, literally everything. Okay, let me show you how. Okay, now see, you have this point A and you have this point B, right? So what is the quickest path between A and B? It's all medium is clear, right? It's the straight line. Now this concept is actually called rectilinear propagation of light. You have heard this name before? It's a big term, but this is all it means, right? Rectilinear propagation of light. So, okay, the next is, if you're traveling from A to B in rectilinear propagation of light, what is the quickest path from B to A? That's also this path. Okay, so what you travel in this path is actually equal to what you travel in this path. So this is actually called principle of reversibility of light, RPL and PRL. Okay, so you have proved two different theories using just a single assumption. Now, in your lower standards, you have learnt about a concept called the laws of reflection, right? And they taught you that it's a law, remember it. So the angle of incidence equal to angle of reflection. But why? If I ask you why, will you be able to give me an answer? Right? Will you be able? Okay. So let me give you an answer to this. Okay. So what I told you that light is always in a hurry, right? Okay. Okay. So let's build this. You have a mirror. You have a mirror. You have a rod here, and the rod is being reflected, right? So this distance is actually equal to this distance, correct? You have another rod of same height on this panel. Okay, now what is the quickest path between this point and this point? To understand this, we will generally, what we'll do is we will try to find out the quickest path between this point and this point. So what is the quickest path? By RPL, that's the straight line connecting these two, right? That's a straight line connecting these 2 points. Okay, and since this is a flipped version, this is a flipped version of this thing, so the quickest path between this point and this point is basically of equal length. So this is just directed here, right, where this length and this length is also equal. Okay, and we know that this angle is 90 and this is 90, and this side is common as well, right? So these triangles are congruent. Okay, now we also know that this angle theta and this angle is also theta because they are alternate angles. And by the principle of reversibility, any path you go from here or here, or you go from here to here, the angles will be preserved, right? Okay. So if they are alternate angles and these two triangles are congruent, then this angle is also theta, right? Now let's build a perpendicular. Okay. So you have a perpendicular where this entire angle is 90, this entire angle is 90. So this entire angle is 90 and this entire angle is 90. Okay. So if this is theta, then this is 90 minus theta, right? Also, if this is theta, this is also 90 minus theta. So what did we just prove? We proved that angle of incidence I is actually equal to the angle of reflection R. Okay, and that's your laws of reflection. You just proved it based on a single assumption that light travels to tend in the quickest possible path. Okay, cool. Now, this was your class 9 physics on light. In class 10, we will learn about a concept called refraction of light. And to understand that, let's first talk about the speed of light. Speed of light. Okay. So the speed of light, it is the fastest thing in the universe, and it actually moves with a speed equal to c, that is basically equal to 3 into 10 to the power 8 meter per second, right? This is the speed of light in vacuum. Okay, light moves in the speed in vacuum, correct? But what happens when light moves in a medium, right, which is not vacuum? It has some matter in it, right? Okay, so light basically tends to move slower in a medium, right? Light tends to move slower in a medium. Why does this happen? Okay, so let us understand this fact. So we know that mediums are made of matter, right? Okay, and matter is made of atoms. So when light enters a medium, it actually hits the atoms, and what atoms do? They absorb this light, and after absorption of this light, they re-emit the light. Okay, they re-emit the light in a different direction. Okay, and this absorption and re-emission causes a delay in the speed of light, right? Because absorption takes little time, re-emission takes a little time. So actually, in effect, the speed of light is reduced. Okay, the speed of light is reduced in a medium. Now, as the speed of light is reduced, and as light is always in a hurry, light in a hurry, so what it will try? It will try to spend the least amount of time in this medium, right? It will try, where your speed is less, you will try to spend the least amount of time in that region, right? You will try to go to a different medium. So if this is the speed of light, light is moving fastest in this medium, it enters the medium. If it had to go in this medium, it had to follow this path. So what it does is, light bends, and on bending, it has to spend least amount of time here, right? So this was the original path. If it had moved here, it would have gone with this path, but light actually bends to spend the least amount of time in this medium, and it comes up, right? This phenomena is actually a surface phenomena, and it is termed as, any guesses? Yeah, it is termed as refraction of light. It is termed as refraction of light. Okay, but you might ask me, how does light know how to find the quickest path? Or in that matter, how does light know to traverse in that quickest path, right? So light basically has different speeds, and depending on that speed, it decides to travel which path it has to take. Also, the emission and reabsorption bends light. Okay, now why this happens? Okay, due to the property of a medium, and also due to the atoms in that medium. So how do we represent the property of a medium and atoms of this medium with context of light? We define a quantity called optical density. Now what is optical density? Optical density is basically the measure of how or by what extent a medium bends light. Now this optical density is not to be confused with mass density, your normal density. To give an example, let's take a bowl of water, okay, and in top of that you take oil, right? Oil has lower mass density than water, and so it floats on water, okay? But light light travels faster in water, and that's why you can see things clear in water. But here on the oil, it takes much more time, okay, and it is more optically dense than water. Okay, so more the optical density, more will the light bend, because it wants to spend the least amount of time in that medium. So greater the optical density, it implies that the bending of light or refraction will be more in that medium, and the light will spend the least amount of time in that medium. So this question often comes in your competitive exams as well. If you know this relation between optical density and the speed of light, you can very well secure marks there. Okay. Okay. Now then comes a question that how we see things, right? How we see things. So some philosophers used to say that light actually comes out from our eyes, and that's how it reaches things, and that's how we see things. Okay. But if this was true, we would have been able to see things at night, because light is coming out from our own eye, and we would not need any source of electricity or something. So this is not true. What is true is an object, it reflects light, it absorbs some light, and it refracts some light, right? When light reflects off surfaces, it reaches our eye, and that's how we pinpoint its location of where it is, and that's how we see things. So due to reflection, light bends, and light bends and reaches our eye, and we see things. Similarly, due to refraction, light bends when it travels from one medium to another medium, and that's how we see things in different medium. Okay, so you're standing on land, you're seeing things in water, that's because of refraction. Okay. Okay, cool. So if this is true, one more derivation from this, that if you have two mediums, one is more optically dense than other. This is medium 1 and this is medium 2, and this is the medium boundary. Suppose one medium is more optically dense than medium 2. So if this is true, refraction will happen in such a way, when it is moving from a less optically dense medium to a more optically dense medium, it will bend towards the normal, and by the principle of reversibility, if it is moving from a more optically dense medium to a less optically dense medium, it will move away from the normal, right? So in this path it is moving towards the normal, right? In this path, right, it is moving towards the normal, and when it goes from here to here, it will move away from the normal. Okay, cool. This is true. Now let's define some angles. This is I, this is R, right? So as you see that the speed of light is more in that medium where this angle is greater. So this I is basically directly proportional to the speed of light in that medium, right? We represent it by Vm. Okay. Now also we know that I is directly proportional to sine of I, right? I is directly proportional. As the angle increases, its sine value also increases. Sine 0 is 0, sine 90 is 1. Okay, so as angles increase, their sine also increases. Okay, so I is directly proportional to sine I. Okay, from these two, if we take a ratio, then we will get that sine I by sine R is actually equal to speed of light in medium 1 m1 by speed of light in m2, right? Now it turns out that this ratio of V of m1 by V of m2 holds true for any angle of incidence and for any angle of refraction. So I forgot to define this angle. This is the angle of incidence and this is the angle of refraction. So for any pair of I and R between these two media, this ratio of Vm1 is to Vm2 is constant, right? And this is represented using a factor which is known as the refractive index of medium 2 with respect to medium 1. So how do we write it? We write it using the symbol mu of medium 2 with respect to medium 1. Okay. Now what this means is the refractive index between a pair of media gives the ratio of speed of light between medium 1 and medium 2. Okay. Okay. Now this law is actually the law of refraction. Okay, you learnt about laws of reflection. This is the law of refraction, and this is actually called Snell's law of refraction. And along with this, the angle of incidence, the angle of refraction, and the normal, okay, they are always on the same plane. Okay, so basically you have proved the laws of refraction as well from that simple theory that light travels in the quickest path. Correct. Cool. Okay, so greater this ratio, more the light will bend. Okay, and more the it will go towards the normal or away from the normal, depending on that. Okay, now suppose you have 10 different pair of medium, right? You have medium 1, you have medium 2, you have medium 3, and you have 10 different medias, right? And you want to find out the refractive index between each of these mediums. Okay, now this is difficult, right? Because for 10 different media you need to do 45 different experiments like this in order to trace the refractive index between these media. So what do? Do we actually do this 45 experiments? No, we don't, right? We actually calculate the refractive index between these medium and the vacuum, right? And the vacuum. Okay, so we actually need to do 10 different experiments. Okay, we need to do 10 different experiments for 10 medium. We are calculating 10 different refractive index, and this refractive index with respect to vacuum of a medium with respect to a vacuum is called the absolute refractive index. Note this down, please. It is known as the absolute refractive index. Now in your books, this is just a term and you need to remember this term. But why to remember this term? So you know that this term has actually been invented because if this wasn't invented, we had to do 45 different experiments, but now we are doing just 10 different 10 different experiments. But does it solve the problem? We are knowing the refractive index of a medium with respect to vacuum, but how can we calculate between these two different pair of media, right? Turns out, okay, so firstly let's build this refractive index of a media is basically the speed of light in vacuum by the speed of light in that medium, right? From the previous Snell's law that you had noted down. So with respect to vacuum is actually the speed of light in vacuum by the speed of light in that medium. Okay, this is called absolute refractive index. Correct. Okay, let's grab this. Yeah. If you know the absolute refractive index, from here you can derive two conclusions. Firstly, the refractive index of a medium is inversely proportional to the speed of light. Obviously, right? More the refractive index, more the optical density, lesser the speed of light in that medium. Okay, one is this. Secondly, suppose you have two different medium, one is glass, one is water, right? One is glass, one is water. So how do you build this? This is absolute refractive index. So C by V of velocity of uh, light in glass. This is C by velocity of light in water. Now C is the speed of light in vacuum. So these terms cancel out. Okay, let's actually clear this out. Clear this space and use this space. One second, just a second. Let's clear this space. Okay. So if you simplify this, you will get mu of G by mu of water is actually C by Vg into Vw by C. Now this cancels out and you get the okay mu of this as well. Okay, good. So what you get is the refractive index of mu of G by mu of W is actually equal to V of W by V of G, right? Also a derivation from this as well or from the ratios directly. This is how we find the refractive index between two given pair of media. This term is called the refractive index between glass and water. So this is glass, this is water. This is to understand and to expand this. If you have to have a medium 2 with respect to medium 1, what you will do is you will write the speed of medium 1 and divide it by the speed of medium 2 because they are inversely proportional. Okay. Okay. So the entire Snell's law now, which is not given in your books or might be given depending on what book you're following. So Snell's law, the entire Snell's law is sine of I by sine of R equal to V1 by V2 equal to mu2 by mu1, where mu m is inversely proportional to 1 by Vm and is actually equal to C by Vm, right? So this is the entire Snell's law. I hope that this is not given because this won't be generally given. This entire thing won't be given, but it is important for your board exams as well as for your competitive exams. Okay. Okay. So you have actually understood the entire concept of refraction from this one concept that light is always in a hurry. Okay. Now let's talk about applications. Okay. So given that this medium is more optically dense than this medium and you have an object in this medium, so when you have a light traveling from this medium, when it goes out, it will move, yes, it will move away from the normal, right? Because optical density of m2 is greater than m1. Okay. So now let's increase this angle. Okay, what will happen if this angle is increased? This will also be increased. It will move more away from the normal. Okay, now there comes a point when you hit the surface at an angle that the refracted ray is totally parallel to the surface. Okay, none of the light comes out. This angle has a specific name. It is called the critical angle. Critical angle between the two pair of media. In this critical angle, the angle of incidence is c, and it's capital C, guys, not to confuse with the speed of light. And the angle of refraction is actually 90 degrees because 90 degree to the surface. Okay, so this theta is actually 90. Okay, so by Snell's law, sin C by sin 90 is equal to mu of 2 by mu of 1, which is equal to V of 1 by V of 2, right? So simplifying this, sin 90 is 1 just. Okay, so this is actually equal to mu of 2 by mu of 1 and is equal to V1 by V2, correct? Okay, cool. So this is called the critical angle, and you have this critical angle. When you have this critical angle where the medium 1 is air and the medium 2 is water, right? What you do is this sin C is inversely proportional to the absolute refractive index. Okay, remember this. Cool. Now what happens when this angle is further increased, right? You are hitting the surface with an angle greater than the critical angle. If you are hitting the surface with an angle greater than critical angle, okay, let's clear things out. What happens if there is a surface? You hit the surface with an angle which is greater than the critical angle. The entire light gets reflected back into the same medium, and this phenomena is termed as total internal reflection. And you basically use this concept for transmission of internet through optical fibers and all that stuff, right? Why do we use it? Because there is no loss of energy, right? Because the entirety of light is being reflected back into the same medium. There is no loss, right? In normal reflection, there is some part of light that is absorbed, some it's refracted, and the other thing is reflected. But here, the entirety of light will be reflected back. So in optical fibers, they hit the fiber with an angle greater than the critical angle between the two pair of media. And actually, okay, just a second. And actually, the light goes like this and it travels through the media till it reaches the destination. So that's an application of total internal reflection. Okay. So now you have understood total internal reflection, you have understood about critical angles, you have understood Snell's law. Now finally, we will have an application of refraction, right? So suppose you have a glass slab. Let's take a glass slab first. Let's take a glass slab. Okay, cool. You have taken a glass slab. Now let's draw some. Um, yeah, let's draw. Suppose you have a light. Light has entered from this medium. If this medium wasn't there, it would have just directly, just a second, it would have just directly followed this path and would have come out, right? But there is a medium, right? There is a medium. So this light, this is I1, this light will be bent, right? This light bends. Okay, let's call this angle R2, R1. Okay, again, this is the medium again. This is the medium again. This is the angle of incidence again. Now let's call this I2, and this is actually moving from a denser medium to a rarer medium now, so it will move away from the normal, right? Okay, cool. Let's denote this angle by R2. So you see that light is entering from a rarer to a denser medium, so it is going towards the normal, and then again it is going from a rarer medium to a denser medium, so it is going away from the normal. Now you see these two rays are parallel, right? So the light isn't the light isn't deviated. Sorry, it isn't angularly deviated. What this means is it is parallel to the emergent ray is parallel to the incident ray. Okay, that what does it mean? Okay, but it is displaced. You see that this is displaced, and this displacement, we have a term for this. We call it lateral displacement. Lateral displacement, but it isn't deviated, right? We'll prove that this is not deviated. Just a second. But this lateral displacement depends on the refractive index, depends on the thickness of the glass, because more the thickness, more will be the angles. Okay, and also depends on the wavelength of the light used. Okay. So now let's prove that these two angles are equal. Okay, so firstly, these are parallel lines, right? These are parallel lines. Okay, so these are parallel lines. So if you have a transversal cutting this, so this is a z angle, right? This is what do you call it? You call it reflex angles, right? This angle and this angle are equal. So in this case, this R1 and this I2 are equal. R1 and I2 is equal. Okay, R1 and I2 is equal. From Snell's law, we have sine of I1 by sine of R1 equal to, this is air, this is glass. So this is equal to mu of G by mu of A, right? This is glass and this is air. So for this media, this is sine I2 by sine R2, which is equal to mu of A by mu of G, right? Direct application of Snell's law. If these are true, from these two equations we get that sine I1 by sine R1 is basically equal to sine I2 by, sine R2 by sine I2, correct? If this is true, we know that R1 and I2 are equal, so this sine of R1 is also equal to sine of I2, so this cancels out. So what we are left with is sine of I1, sine of this angle, and sine of this angle is equal. If their sines are equal, so these angles are equal. Sine theta is equal, so I1 is actually equal to R2, and as they make the same angle with the normal, so these rays are actually parallel. So we have proved that there is no deviation in the path of light when it's moving from one medium to another. It is just laterally displaced for plane surfaces, of course. Okay. Okay, now this can be extrapolated when light has different mediums, right? Okay, just a second. Light is passing through a combination of mediums. So suppose there is a glass slab and there is a ice slab, right? Light is passing from here and it is coming out somewhere here. These rays will also be parallel because see, in between this glass slab and this is the glass slab and this is ice. Okay, so in between these two pair of media there is a infinitely small amount of air, so we can draw this like this. Okay, you can draw this like this. Light is coming here. When it is moving out of the glass, it is moving parallel. Okay, it is moving parallel to the incident ray. This ray, when it enters the ice, it will move away from the ice and it will finally come out, and this will be parallel to the parallel to this ray. Okay, so this ray is parallel to this ray. Let's use a different color. This ray is basically parallel to this ray, and also this ray is parallel to this ray. So these two rays are parallel. Okay, for a pair of more than two medium. Okay, okay. So if you have come this far, you deserve a pat on your back because you have done a lot of concepts. Now, finally, for the final concept, we'll talk about apparent depth and real depth, right? Apparent depth and real depth, and we'll finish off. Excuse me. Okay, real and apparent depth. We'll prove this in the next class, but for now, when you have, suppose you have a friend who is standing on water and you are seeing him, you will see that his legs appear shorter. Okay, we will prove this. You're on land and you see your friend, you see that his legs appear shorter. Why does this so happen? If light would have directly come out, okay, just a second. If light would have directly come out, you would have seen like this. Okay, I am not good with drawing straight lines. If this was land, you would have seen this, but due to refraction, what does has happened is, when you go here, light comes out in this path. Okay, light comes out in this path, it is actually deviated away from the normal, right? Because it is light is moving from that object. Okay, this is the object. Okay, let's draw it here. This is the object, his legs. Light is coming out from water to air. It is deviated away from the normal, right? Deviated away from the normal. What does your eyes see? Your eyes turn this point backwards, right? Your eyes see him somewhere here. So this is the apparent depth, while this was the real depth, right? So this is apparent depth, this thing, and this entire thing is the real depth. So his legs appear shorter. Okay, this also takes place due to the phenomena of refraction. Okay, so there occurs a shift. This is the shift, right, in between apparent and real depth. Real depth minus apparent depth is called shift, and we will prove this apparent depth is actually equal to real depth by the refractive index between this medium. Okay, this medium and air, right? Okay, so the shift is basically d times 1 minus 1 by mu. We will prove this entire thing in the next class, just a heads up. Okay, and that's how you see things like this. That's how stars are seen in a different position, and also this is why your pencils, if you drop a pencil in a different medium, you will see that the length of the pencil is shortened or the pencil is bent. You have some reasoning in your board exams, they give you these reasonings. So this happens due to the refraction of light. If you know, if you just write down these reasonings, you straight away fetch 5 marks. Okay, so these consequences are seen in twinkling of stars. In these consequences are also seen in mirages, where mirage is formed due to this shifting of depths, and also due to total internal refraction. So coming to the end of the class, we have covered a lot of concepts just from a single assumption that light is in a hurry, Fermat's principle. From Fermat's principle, we proved a lot of theories regarding rectilinear propagation of light, principle of reversibility of light. Also, we have proved the theories of reflection. We have talked about refractions. Then we have introduced some certain terms. Then we have derived Snell's law. We have looked at applications of critical angle and total internal refraction. We have also looked at the concepts of real depth, apparent depths, also rectangular glass slabs, lateral displacement. So you have learned so many concepts in such a small amount of time, all using the small assumption that light is always in a hurry, right? So I hope that you had fun. Me signing off. I am rudrajit. I hope you guys had fun. I had fun teaching you guys. Thank you.